Welcome to the webinar, Financial Benefits of Creating an Effective Alarm Management Program. My name is Todd Stauffer. I'm the Director of Alarm Management here at Exida. And first, a little bit of background about Exida as we start this presentation. We were formed back in 1999 by a couple of gentlemen that wanted to make the world a safer place. And in this case, by world, I mean process industry plants, factories, refineries, chemical plants, areas like that. And they did that initially through developing the discipline of process safety or functional safety with training, assessments of instrumentation to determine their safety capability. They developed software for SIS design. In the last couple of years, we've expanded that scope to now include cybersecurity as well as alarm management, two other areas that overlap with process safety and are consistent with the vision of making the world a safer place. So with that, let's talk about alarm management, which is the topic for this webinar, and creating an alarm management program, alarm management improvement program. In this webinar, we'll talk about why you might want to create an alarm management plan, what goes into creating a successful one, how you define it, the keys to success, how you maintain it and deliver benefit, how you measure the benefit. And then for the final portion of the discussion, we're going to look at how you can calculate or determine the financial impact of a successful alarm management program. And we'll walk through a series of questions, and you all can post your own assumptions or recommendations for the different numbers that would go into the calculations so that you can follow along and do the calculations for yourself relating to your particular plant situation. So with that, let's get started. So why might one create an alarm management improvement plan or a program? Well, if you have not done one of these before, or you've not gone through an alarm rationalization, which we'll talk about what that means shortly, then chances are your operators are getting too many alarms. They're getting overloaded with alarms, whether it's steady state or whether it's after an upset, an alarm flood. And of course, when you get more alarms than you can realistically handle or deal with, something's got to give. So they're going to miss alarms or make mistakes. We're potentially putting them in a situation that could lead to failure. Another significant problem is subjecting them to nuisance alarms. Different types of nuisance alarms include chattering alarms, standing or stale alarms, bad actors, redundant alarms. And these are really bad because they, again, get in the way of the operator performing their job effectively. And they do that because a nuisance alarm, the operator does not necessarily need to respond to. They may respond to the alarm and it may not actually correct the situation. So once they realize that there are alarms that are occurring that don't have an impact or don't have any consequences, they get used to the fact that they don't have to respond to alarms. And that is a bad practice to develop. Unfortunately, it's not, it's what the operator needs to do to be able to address the overload of alarms and meaningless alarms that they get. But ideally, we don't want them to think that any alarms are unimportant, that any alarms don't need to be responded to. So that's a key thing that we need to address in a program. We also want to look for alarms that don't have any kind of response to them. As we'll see, that doesn't really meet the criteria or the intent of being an alarm. We'll also look for alarms that have an incorrect priority, because priority is what the operator is supposed to be able to use to know which alarm is more critical than another. So when you've got multiple alarms at the same time, how do they know which one to respond to first? So we want to make sure that that is done. Now, let's talk about what this can do, these alarm management issues can do to an operator. Now, operator's job is not to be responding to alarms. Their job is really to run the plant as efficiently as possible, maximize throughput, maximize quality of the product, minimize downtime. So their role is really to do that. And one could think of the responding to alarms as an unnecessary interruption of that. So part of what we want to realize is alarms truly are an interruption to the operator doing what they're supposed to do. So they should only come up or be presented to the operator when there is a critical situation that truly warrants their attention. Because the constant responding or looking at alarms and figuring out whether it's a nuisance alarm or a real alarm takes a lot of mental processing of the operator and takes away their efficiency and ability to do their real job. So other reasons why alarm management program would be important, certainly if an operator misses a critical alarm, because of the reasons we just talked about, that can lead to unplanned downtime, damage to equipment, people could get hurt, incidents, accidents, loss of product, lower quality product, a lot of different things. So then there are other external influences related to pushing to create an alarm management improvement program. Your corporate or risk management department, maybe from headquarters, might be pushing to implement a program. Insurance companies look to make sure that folks are doing this, as well as regulatory agencies. So there are a lot of different ways that the motivation can come about. Good news is there is a standard that exists for alarm management that tells you what you need to do. So the ISA 18.2 standard, which was released in 2009, defines the requirements and the recommendations for what you need to do to have a successful alarm management improvement program. And it defines it in the terms of an alarm management life cycle. If you're familiar with the functional safety life cycle, you'll understand how this works. But basically, it's a layout of the different activities as part of an alarm management improvement program that need to be executed and how they all interrelate to each other. So adopting the alarm management life cycle is really the critical key to being successful. Now, there is actually a new alarm management standard that was just released 2 weeks ago. Now, this is an international standard. It's an IEC standard. So if you are listening from outside of the U.S. and you thought that you didn't really need to pay attention to the ISA standard because it was just a U.S. standard, that's not really the case anymore. There's now an international standard which was created based on the ISA 18.2 standard. So now there's a consistent methodology for alarm management around the world. Now the ISA standard is actually accepted by OSHA here in the U.S. as recommended and generally accepted good engineering practice. So it's basically what you need to be following if you are a PSM site for OSHA or to demonstrate just good engineering practices. Now, one of the things that the standards do very well is define common terminology. And one of the most important terms or definitions defined in the standard is what an alarm is, the definition of an alarm, what an alarm is supposed to be. And we're going to go through this really quickly. An alarm is supposed to be an audible and or visual means of indicating to the operator. And I underlined the word operator because the alarm system is really for the operator. They are the owners of the alarm system. All of the information that comes through the alarm system must be understandable and actionable by the operator, or else it should not be in the alarm system. Should also indicate an equipment malfunction, process deviation, or abnormal condition. An abnormal condition is underlined to reinforce the fact that alarms should be used to indicate that something is wrong, something unexpected has occurred. We also include in that definition then that an alarm requires a response. And I don't mean silencing the horn. I don't mean acknowledging the alarm. I mean opening a valve, turning on a pump, something like that that's going to address the abnormal situation and hopefully correct it. Now, what you'll find is if you go through all the alarms that you have in your system, if you just make sure that everything that's in there that's presented to an operator meets this definition of being an alarm, you will solve 80% of your alarm management problems. In fact, the issues that we just looked at, the issues list, stems from alarms that don't meet this definition. Now, one of the other things as part of the program that we want to talk about is all of the information that the operators do get in addition to alarms. Informational things, interactions via prompts and messages. So one of the important things is that you're able to segregate out alarms versus non-alarms and ensure that things like alarm summary display lists include only alarms. So information that requires an operator action and represents an abnormal condition. Those are the only types of events that should appear in the alarm summary list. Now, that doesn't mean that some of this other information, alerts or prompts or messages, isn't important. It's just that it should not be within the alarm system, because we want to condition the operator that if you get an alarm after you've performed this program, that it is mandatory that they respond to that alarm. So obviously that would be self-defeating if we put some non-alarms in that list that they didn't need to respond to. Some other key design principles: we will actually document what the operator is supposed to do during the rationalization activity, which is where you go through and assess and make sure the alarms actually meet that definition that we just looked at. And if we can't define what the operator should do for an alarm, their response, then that point really should not be an alarm. We also want to make sure the operators have enough time to respond when the alarm occurs. And this means not too much time and not too little time. We also want to make sure then that any time an alarm is presented to the operator that it's useful, relevant, and unique. You know, certainly alarms that would come from equipment that's out of service are not going to be useful. Alarms that are expected, cascading, redundant alarms that occur in a pattern every time another alarm occurs are not useful because they're not unique. We also want to make sure that we're not presenting the operators with more alarms than they can respond to. There are limits from a human factors point of view, the bandwidth that humans can assess information and deal with it. And in fact, a lot of the elements of HMI design and human-centered design focus on maximizing that bandwidth, but there is certainly an upper limit to what humans can do. And we also want to make sure alarms are prioritized appropriately. Now, to create an effective program that follows the alarm management lifecycle is going to require leveraging capabilities within your control system, within your DCS, and in some cases additional tools from third-party suppliers, from the DCS supplier. In this case, what we're showing is for an example DCS. We'll use the Emerson Delta V system as our reference point. The products and capabilities within the DCS that we'd want to kind of assemble to create our alarm management improvement program. And it includes the SoAlarm tool from Exida, which is a tool for alarm rationalization. In the Delta V system, it has some inherent alarm management capabilities that we'll leverage and we'll talk about. Shelving. It's got an optional thing called Alarm Help, which allows you to present information to the operator to tell them what to do. And then there's some tools available to actually measure and monitor your alarm system performance. And when I say performance, I mean the number of alarms that the operators are getting per day. And then we also have a template to help folks create an alarm philosophy document. So let's talk about what the program would actually look like. Consistent with all good self-help programs, there are 7 steps to our alarm management program. It wasn't actually done that way on purpose. That's just the way it turned out. The idea of creating certain steps to map or relate to the alarm management lifecycle. So let's go through this briefly, and then we'll touch on each of these stages a little bit more later. It starts with some assessment of where you are from an alarm management point of view. So some initial benchmarking of your performance and the processes that you have in place, followed by creation of an alarm philosophy document for your site. That's the guidelines for doing alarm management at your site. Once that's in place, then you can move into the continuous improvement mode by performing alarm rationalization. And we'll talk about what that means. Implementing the results of rationalization in the control system, perhaps also implementing advanced alarming, some alarm suppression techniques within the control system, and every so often, perhaps on a monthly basis, measuring your alarm system performance to see whether the changes that you've made have had a difference or impacted a difference in the control system performance for the alarm system. And then the last step is an audit to basically review the processes and the way things are working to make sure that the alarm system and the program is proceeding in the direction that you were looking for. So now let's look at some of those in a little bit more detail. And the first step is the benchmarking, or the performance, establishing a performance baseline. If you're going to do process improvement, one of the first steps you need to do is baseline where you're starting from. That way you can see where you are. We'll show some metrics that you can actually compare to. And you can also then use that as the reference point for showing how much better you've made things as a result of your program. So we want to baseline performance and the processes that are used. For example, management of change. Are operators allowed to change alarm limits and disable alarms on their own, or is there an authorization and review process required? So we want to look at those kind of things as part of this benchmarking. We're going to do it from a qualitative and a quantitative point of view, and I'll indicate a little bit more about what that means. And part of what we're looking for, besides establishing the baseline, is the common issues that we need to address. So what are the issues that the operators experience that need to be addressed as part of the program, either during rationalization or in development of the alarm philosophy document? Now, the ISA standard defines some key performance metrics that we can use for the purposes of figuring out where we are. So, for example, here we can see the number of alarms per day or per hour that is recommended, which when you do your performance baselining or benchmarking, you can compare against. So the ISA standard says operators really should not get more than 300 alarms per day, which averages out to be 1 to 2 alarms per 10 minutes. So with that factor in mind, we can easily measure the performance and compare to it with a pre-made tool, or a tool created for the purpose. Now, for a Delta V system, there's a tool called Delta V Analyze, which can run reports and create those performance metrics for us and actually show you the comparison to what ISA recommends. So it's right there in front of you. So here's an example of seeing the number of alarms per day for the operator. We can also then look at the number of alarms that occur after an upset or an alarm flood. If the steady state amount that an operator can deal with on a long-term basis is 1 to 2 alarms per 10 minutes, anytime we go above 10 alarms in 10 minutes, that's considered an alarm flood. So we can look for how frequently that occurs and how bad it is. Another very useful measurement in your initial baseline is looking at your frequently occurring alarms, or looking at which alarms are the most frequently occurring, with the idea that you may have 10,000 alarms configured in your system, but there's probably 10 or 20 of them that create 50 to 80% of all the alarms that the operator sees. So if you can pinpoint them, that obviously gives you some great starting points to fix right away in your improvement program. So it's some low-hanging fruit. Certainly to address 10 to 20 alarms and reduce the alarm load on the operator by 80% is definitely going to make a difference, and people will notice it. Now, I said we're going to do quantitative measurements, and that's what we just saw with that tool, but we also want to do some qualitative assessments, primarily interviewing the operators to see how well the alarm system works for them. And this would be looking for things or looking at their input in areas that a tool really can't help us with, a measurement tool. So things like, when alarms are presented to the operator, do they understand the message that appears? In many cases with abbreviations and things like that, you'll find that the operator doesn't really know what that means. So we want to know that stuff before we get started, because that will be something that we'd want to fix. And here's an example of what we learned from an assessment of a bunch of operators. We asked 8 of them, what percentage of alarms do they get that they believe are for information only and don't require an actual response? So essentially are a violation of the definition of what an alarm is supposed to be. The answers were kind of varied across the board, but on average it was like 50%. So that meant 50% of all the alarms that the operators get really aren't alarms. So obviously that's a key learning that we can use to drive performance improvement. Now it went further in some of the more astute operators judging and providing feedback that there's actually one alarm type, a change from normal alarm, that occurs anytime they activate a pump from an HMI faceplate. And they said, that's really kind of crazy. I'm turning on a pump myself, and I get an alarm within the DCS that tells me that the pump has started. Thinking about what an alarm is supposed to be, that's definitely not it. So that was great feedback or information for us to use to define a better way to do things. And we want to codify the better way to do things in an alarm philosophy document, which is essentially a guideline for how to do alarm management stuff at your site. So it's going to contain information like, what's the criteria to determine whether something is an alarm or not? How do you prioritize it? What colors will you use in the HMI? What's the MOC process going to be like for potential alarm management changes? So a lot of things that need to go in that philosophy document. One of the most important things is how you will prioritize alarms. So here we have an example of what's commonly used. It's a matrix of consequences in different areas, so different impact areas, very similar to a PHA risk matrix. And essentially during rationalization, what we'll be doing is evaluating the priority by assessing how bad the consequences are in these 3 different areas, and then matching that up with an estimate of how much time the operator has to respond. Let's say that the worst case consequence was major, and we had a 15 to 30 minute time window. That would dictate what the priority would be. So we want to define this matrix before we start rationalization, so it's not a debate over what priority things should be. There's a consistent, objective methodology for defining the priority. Another key thing to talk about during development of a philosophy is alarm suppression, in particular for the operator, which is called alarm shelving. So this is manual suppression. More and more DCSs support this as a native function. Interestingly enough, one of the changes between the ISA 18.2 standard, which came out in 2009, and the new IEC standard is that the IEC standard actually made alarm shelving a required capability to be in the system. So that means that your DCS vendors, if they don't have this capability there now, they will have to build it in. So there's a reason why it was felt to be so important, and that's because this is a key tool to help the operator deal with alarm upsets. So to be able to remove the nuisance alarm from their field of view. And alarm shelving doesn't permanently disable an alarm. The idea is it's removed from their point of view temporarily for a fixed period of time and then comes back after that time is up. So it's an effective tool to help operators deal with things like nuisance alarms. Now, in a lot of cases, I've talked to clients that are a little bit concerned about giving the operators the ability to suppress alarms. And are thinking about the way things work now, where you have a ton of nuisance alarms. Part of a good alarm management program is really going to result in a paradigm shift. And that would be evident in the use of shelving. That operators, once you've given them a new system that only alarms when something is important, that's when the ability of this shelving becomes useful. And then they need to realize that this is a powerful capability and should only be used as appropriate. As part of the definition of the philosophy, we want to define what is appropriate. So there may be certain types of alarms that should not be shelvable, maybe your most critical priority alarms or those related to safety. So you want to define all that and come up with the method for alarm shelving that meets your requirements and your comfort zone. And Exida has a template that we've created to help folks create an alarm philosophy document that's tailored to their operational requirements, which can be used to create that relatively quickly. So now let's move on to the performance improvement phase. So we need to have that philosophy document done before we can start. And where we're going to start is with alarm rationalization, which is where we review the alarms that are either in your system now or are proposed for a new system. And we want to make sure that there's a good reason to have the alarm. We're going to look at what's the purpose of this alarm. Is it really needed? Does it serve a purpose that's beneficial to the operator? Again, looking at it from the operator's point of view. So we'll go through and we'll actually document that information related to the alarm. We'll look at determining what the priority is, and we'll document that as well. And the term that's used for where this is all documented is called a master alarm database. Now, the Exida Soul Alarm tool acts as your master alarm database, allowing you to record all of the alarm design information, and it actually guides you through the rationalization process. Now, part of the reason the philosophy needs to be created first is because there are some things in the philosophy that are rules that will be applied during rationalization, such as that priority matrix for prioritizing the alarm. So we can take that matrix, however it's defined, and basically code that in or enter that into the Soul Alarm tool, and then we can load alarm information or load the candidate alarms either from the existing DCS configuration, in this case with Delta V using a bulk edit technology, or we can do it from an Excel spreadsheet. And then once it's in the database and we've configured the rationalization rules, then we can begin the rationalization process, which is a series of steps. The first step being to look at whether the alarm is valid or not, then to determine and document what's the consequence of inaction if the operator doesn't respond, the cause, corrective action, how much time the operator has to respond. And those are typically the things that we look at first, because that will help us rule out alarms that are not needed. That'll help us figure out whether the alarm has a good basis or has a good objective or purpose. And if it passes that test, then we continue on with the rest of rationalization, assigning the priority, the classification, looking at the alarm set point, setting deadbands and on-off delays, and then also looking whether there's any scenarios or operating states where the alarm needs to be suppressed or have a different limit and priority. So this is all orchestrated through the Soul Alarm tool and recorded. Now, in the philosophy, one of the things that we want to do is determine or document what's the criteria that we should use to determine whether an alarm is valid or not. And this is what we would recommend as a starting point, and this is what we typically put in alarm philosophy documents. So it's a series of questions that you can ask related to an alarm to quickly assess whether it's valid or not. First one is, Does it indicate a malfunction, deviation, or abnormal condition? If you can't answer yes to that question, then it really should not be an alarm. Second question, does it require a timely operator action in order to avoid defined consequences? Again, it's got to be a yes to that question, or else it shouldn't be an alarm. Then we go on with some other ones. Is it unique, or are there other alarms that we would expect to occur as well? And if there are, we want to make sure that we pick the one alarm that's the best indicator. So that kind of questioning helps us get rid of redundant alarms, a type of nuisance alarm. So this gives us a very quick way to assess alarms that are invalid and remove them from the system and not have to spend any more time in rationalization. Now, alarms that pass through that, then we get into the documentation of the true basis or the purpose of the alarm. So what's the cause for the alarm? What are the likely causes? And of course, we want to make sure that it's an unexpected event, not an expected event. We want to define what the consequence would be if the operator doesn't respond. And we're actually after the direct and immediate consequence that the operator themselves can prevent, not the ultimate consequence that would happen if you had a series of failures of layers of protection. So we actually want the mitigated consequence, not the unmitigated. We want to define the operator's corrective action. And if there isn't one, then obviously it doesn't need to be an alarm. Ideally, we also want to define ways or things that the operator can look at, other process measurements to confirm that the alarm is real, that it's not a false alarm. And as part of this, then, if we can't define a consequence, or if we can't define a corrective action, then likely we don't need that alarm. And using the SIL alarm tool, we can document all of that information so we have it from then on. Now, part of this rationalization process, or a majority of it, is done in a committee type setting with significant representation from operations. And hopefully it's your most senior operators who are helping you define and document these things. So it's also, in some senses, a knowledge capture process, because you're defining what your most experienced operators would do or how they would address that particular alarm. So, based on what we just looked at, the thought process, that methodology, the initial portions of rationalization, applying that would solve some of our alarm management issues that we identified earlier. We'd get rid of nuisance alarms. We'd get rid of alarms that aren't necessary, thus reducing the number of alarms that the operator would see. We'd also remove bad actors and redundant alarms via that thinking, that thought process. So moving on to some of the other steps in the rationalization process, we want to prioritize the alarm, again, for the purpose so that if there are multiple alarms present at the same time, the operator knows which one is more critical for them to respond to first. And we want to prioritize based on assessing the potential consequences if they don't respond, using the rankings from the alarm philosophy document, and the amount of time that's available to respond to the alarm. During this part of the rationalization, we may also define alarm deadbands and on-off delays, deadband being a way to reduce the number of times that an alarm actually occurs to ideally just once. In this picture, you can see that the natural fluctuation of the process variable is causing the alarm to go on and off a couple of times before it's clearly beyond the alarm limit. So we're creating a chattering alarm without a deadband. By putting the deadband in, now this same process history results in only one alarm being created. So we've eliminated the chattering alarm. We've eliminated a type of nuisance alarm, which is part of what we want to do as part of this program. Now, another thing to do when you're completed with rationalization, or something to do with the results of rationalization, is to kind of harvest that information. Because if you thought about what could we provide to the operator to help them respond to each alarm more effectively, it would be things like what just happened, What will happen if I don't respond? What should they do? How do I verify it's not a false alarm? And how much time do I have to respond? And not coincidentally, those are the same things that we talked about and documented during the alarm rationalization process. So what we can do, in this case using the alarm tool, is we can extract that information and create what's called alarm response procedures that can be presented to the operator to help them know, how do I respond to this alarm when it occurs? And in a Delta V system, that's what Delta V Alarm Help does. So essentially now what we're doing is we're taking the information for what the most experienced operators would do when the alarm occurs. That's helping us determine whether the alarm is needed. And then we're taking that and we can make that available through Delta V Alarm Help so that every operator gets to see that. So even the junior operators now get to see the benefit or get to see what the more senior operators would do in that scenario. So again, a list of the issues that we can address by performing those steps in the rationalization process. Now let's look at a couple other scenarios, alarm floods and alarm overloads and trips. Look at how we can define an alarm suppression scheme. So if we take a compressor trip as an example of a alarm flood type scenario, alarm flood would result inundation of alarms after a compressor trip. We can set the system up or define it so that the system will detect that the compressor is tripped, and then we can tell it what alarms should be suppressed when the compressor is tripped. So these are alarms that are only there now because the compressor is tripped. They're valid and useful alarms, but not in this scenario. So we want to be able to suppress them, potentially create a common alarm to tell the operator that the compressor is tripped. And using the alarm tool, it actually allows you to see the safety implications of the alarm. What's its classification? What's its priority? Is it an independent protection layer or a safeguard to make sure that it's okay to suppress the alarm? There may be other scenarios then where we want to suppress the alarm when the plant or the equipment is in a certain state. So state-based suppression, we can define that within the alarm tool as well. And the idea is it's defined within the tool as a specification that's then implemented in the control system. In this case, if the control system is Delta V, there are a series of control modules that have been specially designed for alarm suppression by Exida and Emerson that link to that alarm interface. So when we define an alarm flood suppression scheme in alarm, there's a corresponding set of logic for that information to go to so that the suppression actually will run right in the Delta V controller. So again, defining a suppression scheme and state-based suppression will help us deal with issues like alarm floods and stale alarms. And then when we're done rationalization, we may have, as a result of rationalization, eliminated some alarms, maybe added some new ones, changed some limits, changed some dead bands, adjusted some priorities. We want to get that information back into the control system. So again, looking at our example of a Delta V control system, we would export the alarms out of alarm, and using bulk edit and some pre-created format files, we can import that into Delta V and modify the alarm parameters accordingly based on the results of rationalization. We can also build the alarm help faceplates from that to, again, document what the operator should do in the event of that alarm. Now, the process is not over once you've completed rationalization. Now you're going to get into a series of reviewing, maybe on a monthly basis, what the alarm system performance is, comparing to your baseline that we talked about earlier, and that will show you how much better things have gotten. So hopefully you'll be able to see that, hey, some of the things that we've done in rationalization have directly had a positive performance impact to the operator and the alarm system. So certainly this continuous assessment of alarm system performance and using that as a measure of how much better things are getting, as well as continuing to identify alarms that need to be fixed, is a key part of this whole continuous improvement program. Then the last step in the program is called audit. And that's the purpose of that is really to verify or maintain the integrity of the alarm system. So we want to look at the way the system is working. We also want to look at the processes for alarm management that we've said we should put in place in the philosophy document. So management of change, if there was a specific procedure or protocol that was supposed to be executed every so often, maybe on an annual basis, we want to check a few and make sure that we're actually following the process that we said we would. And if not, we want to ask ourselves why. You know, perhaps there's somebody that needs some additional training, or perhaps the process that we laid out in the philosophy is not achievable and it needs to be changed. So we're really trying to focus on making sure we're ensuring the integrity of the alarm system as part of that audit process. Another task that we would do is to compare the alarm settings in the running DCS versus what's in our master alarm database, the SIL alarm database in this case. So if it's a Delta V system that we're using, we can do a comparison and an audit, and that will show us if there are any settings that are different. So if the operator changed an alarm limit or disabled some alarms outside of the MOC process, then we would capture that definition or that change, and we'd be able to assess what the problem was and determine why that had occurred and take appropriate action. So now let's move on to the financial portion of the discussion, so the show me the money portion. So what we want to talk about is how do we calculate the financial impact, the benefit to the bottom line of an alarm management improvement program. And for this, we will look at 5 different financial factors. The first one is reduction in unplanned downtime or lost production. The second one is increased operator productivity from not having to respond to nuisance alarms on such a constant basis. Third one is reduction in avoidable maintenance of process equipment. Fourth one is production optimization or debottlenecking or increased throughput. So essentially something that improves your production capacity. And the last one is capital savings for SIL requirement reduction. So this means maybe some safety instrumented functions in your SIS that were previously thought to need to be a SIL 2 could now maybe be a SIL 1, because we can add the operator response to an alarm as a valid layer of protection. So let's take a look at this in more detail. And the first thing we want to do, and this is going to hold for the whole series of what we talk about here, is I'd like to get your input on which of those 5 financial factors you think would be the most important. Based on your knowledge and understanding, which financial factor do you think will have the biggest impact on the bottom line? So if you would just take a minute and enter your opinion. There is no right or wrong answer to this question. In fact, I'm sure we could find examples of plants or situations where each one of those 5 was a dominant factor. Okay, looks like we have finished with the poll, so let me show it to you. So it looks like half the people thought a reduction in unplanned downtime was going to be the most significant, and third thought production optimization. So that's good, useful information. Now let's move in and look at those 5 individual factors. And again, I'm going to look for your input on what you would typically assume or you think is valid in terms of the financial metrics or the financial assumptions that go behind each of those 5 factors. In this case, what is the average cost of an unplanned shutdown? And we'll look at the cost in US dollars per hour. So again, if you could take a minute to just quickly enter what you think would be a representative value for unplanned shutdown for your plant or plants that you're familiar with. Give you all another couple of seconds here. Okay, so hopefully now you can see it. Oh, we had a couple people change their vote, but it looks like majority of the people said $100,000 per hour or $20,000 per hour. So that was the assessment. So the majority was 100. So let's say it's between 100 and 20,000. So now let's go through some calculations or look at how we would convert what we're talking about into dollars. We could do it one of 2 different ways. First would be if you could quantify the number of trips that you eliminated by the operator being able to respond more appropriately, not miss critical alarms, and if you could put a cost factor on each trip that you were avoiding, you could come up with a dollar figure that way. But in the case for this example, we're going to look at a reduction in the number of hours that were lost, the number of unplanned hours that we can save or get back because of improved alarm management. So in this case, we're going to assume that our cost of unplanned downtime was $20,000 per hour. So a little bit more conservative than what you all actually said, $100,000 an hour. We'll assume that for this facility that they have typically 3 days of unplanned downtime per year. So that's total accumulated. So that would be 72 hours. And based on some industry studies, which I have the references here and I'll talk about more when we're done, you could reasonably assume that you would be able to reduce the unplanned downtime by 30%. So then we can do a simple calculation of the reduction in cost based on being able to eliminate 30% of the hours and what their hourly cost is. For this example, it comes out to be $432,000. And remember, that was with the more conservative $20,000 per hour. If your cost of unplanned downtime is $100,000 an hour or more, you can see that this figure quickly goes up even more. So now let's move on to the next financial metric, and that's increase in operator productivity. So the question is, with improved alarm management, what increase in operator productivity would you think that you might expect? So again, there's no right or wrong answer to these questions. It's just to get your thought and to see what other people think as well. So wait another minute. We have four votes in. Hopefully we'll get a couple more. And then I'll show the results. And you can see that a majority actually said 5%. Some people said 10%. Some people said 20%. For this scenario, we're actually going to assume 8%, so kind of split the difference. So now to do our calculation, we'll assume that you have 2 operators per shift, that you have a 24/7 by 365 operation, and the average burden cost for an operator is about $150 an hour, and we'll get a 8% productivity improvement because now the operators don't have to spend as much time responding to or looking at the alarms. You know, even if they're not actually taking a corrective action, they are spending mental processing time to look at the alarm and think about whether it's a nuisance alarm or not. So we've now freed them up to do other things and to concentrate more on what they're supposed to do. So Certainly, improvement in alarm management or alarm system performance would increase operator productivity. With the assumptions that we just talked about, we can see that we would end up with a dollar figure of about $210,000 with those assumptions. So now let's look at the next financial metric, a decrease in maintenance cost. So what type of decrease in maintenance cost? And the way we'll calculate this is based on your annual maintenance budget and what portion of that, what percentage of that we think we could save based on an effective alarm management program. So we're getting a couple of responses. So far everyone, I was just about to say so far everyone had said 8%. Hopefully you can see the results now. So it looks like majority said 8%. There was one 5%. So now let's look at what we assumed for our calculations. In this case, we assumed 5%. So we were, again, kind of conservative. Now, we could calculate the reduction in maintenance cost two different ways. One would be if you know your cost per work order and the number of work orders that you've been able to reduce. That's one way to come up with it. But for this example, we're going to focus more on applying it to the annual maintenance budget. And in this case, we'll assume that the annual maintenance budget for this particular plant is $10 million. So if we have a reduction in maintenance cost of 5%, we can calculate that that would be a savings of $500,000. Now, is that realistic? Well, certainly, if you've got a better alarm system that's performing more along the lines of the way it should be, that's going to allow faster resolution time. It's going to allow operators to more effectively prevent the control system running in areas that would damage equipment. So I very much believe that you would have a reduction in your maintenance cost because you're able to operate the plant in your normal operating scenarios for longer times. So now let's look at the next metric, which is increase in throughput or production optimization. So what percent, again, would you expect to see from an effective alarm management program? And these are pretty small numbers, but what's amazing is you'll see how big of an impact this can have for a plant that runs continuously. So we've got a couple of respondents. Looks like a majority is 2% or 1%, so let's split the difference and say that it's a 1.5%. is what the poll would say. So let's look at our calculations. Well, we were even more conservative. We assumed a 0.25%. So let's look at the number that we came up with there. Now, if we assume that the actual profit that's created is similar to the cost of $20,000 an hour, and we look at what that would be for a plant that's running 24/7 by 365, and an increase in production of 0.25%, we can do a calculation, and that comes out to be $438,000. So even with that, what appears to be a minuscule improvement of 0.25%, that's adding almost $500,000 to the bottom line. So certainly if it was an even greater improvement, that number would again be higher. So now the last poll question relates to how much capital cost savings you think you could expect from an alarm management improvement program where you're able to reduce some of your safety instrumented function SIL level requirements from SIL 2 to SIL 1. So what do y'all think you could save from being able to deliver that kind of performance improvement? So that essentially means being able to take credit for the operator response to an alarm as a valid layer of protection. And certainly I would recommend or say that if you don't have a well-functioning alarm system, you should not be taking credit for an operator response to alarm. If you have nuisance alarms, if you have alarm floods, if operators are being overloaded by alarms, that would mean that the probability of failure on demand of the operator response would be pretty high, so you would not be able to rely on them. But if you've implemented this program and gotten rid of all those major issues, then you are in a position where your operator response can be much more reliable, or should be much more reliable, due to the fact that there's less alarms. They're more meaningful. If you're providing information on how to respond to the alarm, that will also drive down your probability of failure on demand. So you really can then leverage the operator response as a layer of protection. So, making the results available for you to see, you can see that the majority of people thought that the savings would be about $50,000. So let's look at how that compared to our financial calculations. Oops. So if we were able to reduce 4 safety instrumented functions, and we did assume a $50,000 capital cost savings. So if we were able to reduce the SIL requirements for 4 safety instrumented functions from SIL 2 to SIL 1, we could save $200,000. Now, this doesn't necessarily mean that we're taking a SIL 1 rating for the operator response to an alarm. If you look at a LOPA and the calculations of the probability of failure on demand, depending upon the numbers, a risk reduction factor of 2 or 5 may be enough to make the difference to allow you to go from SIL 2 to SIL 1. It doesn't have to be a risk reduction factor of 10 or higher to have this impact. So now let's look at a summary of where we ended up with these financial calculations. So if we add up all the values for the 5 different financial metrics, you see we come out with a savings of approximately $1.8 million. So the implementation of an effective alarm management program for this representative case was $1.8 million. Now, hopefully you'll see, or you would agree, that the assumptions that we made along the way were not tremendously optimistic. I would say they were conservative in some cases. Some of the percentages that we assumed for improvements were actually less than what you all had said you thought could be achievable. So this number, I would hope, would seem reasonable to you and realistic. Now, certainly, whether the improvement percentage is 5% or 8% or 10% is not necessarily the main issue here. What we just wanted to do was to show you the thinking process, or the rationale, or a way that you can develop this financial model and prove the benefit of an alarm management program once you've implemented it, or actually hopefully use these kind of numbers to say, here's the situation that we are in, and if we do an alarm management improvement program, and if we see typical industry expected benefits, such as what you've seen here, you could determine what the cost savings would be. And maybe that would help get your alarm management programs approved, get them funded. So just kind of summarizing then the business results that we've achieved by creating this program, we defined our baseline for demonstrating performance improvement. We established our goals by identifying issues that needed to be fixed. We created an alarm philosophy guideline to drive consistency in the rationalization and design process. We went through rationalization to remove alarms that didn't belong and to improve the quality of the alarms that are left to make them more meaningful. We documented what the operator should do when those alarms occur, and we're able to present them to the operator in context when the alarm occurs so that they know how to respond. We've implemented advanced alarming to eliminate alarm floods and things like that as necessary. And we've set in place a regular performance improvement activity where on a monthly basis perhaps we review our alarm system performance and see how much better we've made it by our rationalization and design improvement activities. And then we also saw how we can use the audit process to verify the integrity or maintain the integrity. So we've improved operator performance. We've set it up so that we can document the performance improvement over time and the financial benefits. And what you'll also see is once you've cleaned up the alarm system performance, you can actually use the alarm system to drive process efficiency and process improvements. So that's the end of the webinar. We are at time. Very much appreciate you all for hanging in there and attending this webinar. What I've listed here is my contact information if you have any follow-up questions, as well as the references from where that financial input came from. Some of the percentages and assumptions that went in there come from these case studies. So now we have maybe just a minute or two for some questions. So there's one question related to deciding the priority of a high alarm or a low alarm with an automatic shutdown. That's a good question. What I would suggest is perhaps sending me an email about that, and we can talk about that in much more detail. That's almost a 5-minute answer to talk about that. Let's see whether there's any other questions. Okay, I don't see any, so I will say thank you. I'll sign off now. So thank you very much for attending this webinar. Hopefully you found it beneficial and instructive, and we hope that you'll join future Exeter webinars. So thank you and have a good rest of the evening.